Hi, I'm Franklin Nolan. This is Chico State University. Today's date, September 10th, 2015. We have master's thesis statement, a peer-to-peer application using Cache. That's C-A-C-H-E. Rumin Sao, spring 2002. Can be found thesis QA 76 Zeta 468 2002. Zhou, Z-H-O-U. Peer-to-peer application using Cache. A project presented to the faculty of Cal State University Chico. Partial fulfillment of the requirements for degree in Masters of Science Computer Science by Rumin Sao. Spring 2002, peer-to-peer application using Cache. A project by Rumin Sao, spring 2002, approved by the Dean of the School of Graduate Internal and Sponsored Programs, Robert M. Jackson, PhD, approved by the Graduate Advisor Committee, Song Bam Im, PhD Chair, and Melody Collin, PhD. Signatures. Acknowledgements. Thanks, my committee chair, professor, thanks to my, you should say, sorry about that, Chair Professor Songbaim Im and committee member Professor Melanie Claim for reviewing my projects. Thanks my parents, brother, sister in China, flower warring and moral support. Thanks Ru Lan for beautiful wishes. I also received a lot of help from Yu Pan Wu in getting this project done. Many thanks, Yu Pan. Table of contents, acknowledgements, list of figures, abstract, chapter 1, introduction, purpose, project scope, terminology, methodology, outline, background. 2, protocol description, related works. 3, problem solutions, problem and solution. 4, system operations, general description, architecture, system function. Chapter 5, system design, classes, definition, network layer components, file server layer components, service controller, message flow, conclusion, summary, limitations of project, future work, recommendations, reference, list of figures, 18 figures, Gonatella architecture, effective Gonatella network, Pong caching diagram, ping process, loop ping pong process diagram, overall class prototype diagram, over network class prototyping diagram, overall object modeling diagram, connecting sequence diagram, route message sequence diagram, request search sequence diagram, server search sequence diagram, research download sequence diagram, server download sequence diagram, request push down sequence diagram, server push down sequence diagram, share sequence diagram, finally monitoring sequence diagram. 18. Abstract peer-to-peer application using Cache by Rumin Sao, Master of Science in Computer Science, California State University, spring 2002. In extensive analysis of traffic in the Guantel network, it shows that the current ping-pong scheme consumes up to 50% of the total Guantel messaging bandwidth. Moreover, each Pong message returns that a host IP and port number, but many of these return hosts are not accepting connections outside the firewall or unreachable. Ineffective, the careful selection of returning Pong response associated with the Pong cache management would efficiently reduce number of unnecessary network traffic, and current Guantel servants. Such scheme to repeatedly crawl to other nodes in its time to live TTL scope and trying to bring back useful shared information and research consult cache in intermediate nodes will cut the cost of message broadcasting in comparison with simply firing a fresh search to serve only one new query request. Chapter 1, Introduction, Purpose. The project will design a peer-to-peer P2P Guantel servant application and connect to existing Guantel network, and servants will implement the function and are defined in the Gnutella program protocol specifications. Because it conforms to the standards, there is no problem for a servant to join the existing Gnutella network and perform data interchange with servants within Gnutella network. In addition, the servant will implement features that will help reduce servants' bandwidth consumption in comparison to existing servants by using a more efficient mechanism. The goal of this project is to redesign the Gnutella server application by adding a data caching capacity. Because the data interchange in the Gnutella network is through the network backbone of Internet, a well-designed and highly developed Gnutella application is preferred, so it has very positive impact on current Internet performance. This project builds a Gnutella P2P application to address some of the current network traffic issues. Project scope. This project designed a peer-to-peer Gnutella servant application in compliance with the de facto Gnutella protocol. This servant not only follows the Gnutella peer-to-peer standard, but also adopts some of the advanced mechanisms to solve existing problems the current application cannot address. The main functions stated in the Gnutella network will remain unchanged. The intended audience for this project is software engineering interests in developing P2P network programs or to concern with the Gnutella network performance and are wanting to renovate the existing P2P application and protocol specifications. This application was designed using the objective-oriented OO approach. The intended implication language is Java, which is an objective-oriented language. Therefore, much of this discussion will use terminology associated with the OO paradigm. Terminology. Terms widely used in peer-to-peer network application and its projects are broadcasting. Messages are sent, particularly host connected to the source host in the Gnutella network. Firewall. A firewall is a protective mechanism that allows only computers inside the firewall to make a network connection inside the firewall. It will not only outside the computer to make into driven computer networks. If the servant outside the firewall tries to download a file from the computer inside the firewall will prevent this connection from being made. Usually it results in a push request message being sent to the servant inside the firewall requesting the servant connect through the firewall and upload the desired file. If the servant requested the file is also behind a different firewall, then this upload will be blocked and the file transfer cannot occur. 10. GUID, short for Global Unique Identifier. The GUID is a random string that is used to uniquely identify a host or message on the Gnutella network. This prevents the duplicated message from being sent on the network. 10. HTTP, abbreviation for Hypertext Transfer Protocol, a kind of application protocol based on ITCP/IP used mainly in the World Wide Web to define how messages are formatted and data are exchanged. Hops, the number of hosts a message has passed through. Horizon is the group of Gnutella servants that one is capable of communicating with a particular time. Because the decentralized nature of the Gnutella network, the horizon will not encompass the entire Gnutella network. 10. Hosts, the machine that connects to a network and participates in the data exchange activities in this project, has the same meaning as node or peer. Host cacher, when one joins the Gnutella network and sends out ping requests, other Gnutella hosts respond with pongs. The Gnutella software host cache develops a list that keeps track of the Gnutella hosts that sent these pongs. Most Gnutella networks serve some sort of automatic connection feature. These automatic connections are usually made with hosts from host cacher list. 10. URL cache, abbreviation for least recent used cache. LRU and the least recent used will cache be deleted and a new cache needs to be inserted into the cache list. Message, data sent over the Gnutella network. It is one of the 5 types of ping pong. A search request is search reply or a push request. Node, a machine that connects to a network and participates in the data exchange, same as the host. Peer. To compute are considered peers if they are communicating with each other and playing similar roles. For example, a desk computer in an office might communicate with office mail servers. However, if they are not peers, since the server is playing a role of a server and the desktop computer is playing the role of a client, Gnutella peer-to-peer model uses no servers, so the network is composed entirely of peers. Computers connected to the Gnutella network are also referred to as nodes or hosts. 10. Ping. When a new user joins the Gnutella network, a message is a broadcast called a ping request to the host, announcing the user's presence on the network. Node that receives this ping sends a pong back to the pinger using acknowledge they have received the message. 10. Pong. When the node on the Gnutella network receives a ping request or replies with a pong, this contains the response host's IP address and port, as well as the number of files the responding host is sharing and their total size. 10. Port. Each application on the computer that communicates on the internet has specific port number assignments to it. On most servants, the default port for Gnutella is 6346. This means that the servant running Gnutella software is listening on port 6346. However, the user can change the port that is assigned to Gnutella, still be able to communicate with other servants that are listing on port 6346. 10 in brackets. 10 is in brackets. Okay, the port will be exchanged when the computer receives a ping message from the other computer. Push request. When the servant is behind a firewall, other hosts are not able to connect to the servant directly to download a file. When this happens, the host trying to download file sends a push request asking the servant behind the firewall to connect out and upload the file to the host. 10 in brackets. Query, same as search. Query hit. Reply message to a query. Routing. Messages are sent to a particular location. They may pass through intermediate hosts to transist, therefore arriving to the destination. In the Gnutella network, the pong message, the query hit message, and the push message are all routed to the intended recipient. Search. When a servant initiates a search request, it broadcasts a search message to the Gnutella network that contains the query string as well as the minimum speed specified by the servant initiating the search request, also called a query message. 10 in brackets. Search result. When a host receives a search request and has files satisfying the search criteria, it responds with the search result message, and the search result message contains the IP address, port, and speed of servant sending the search result message, as well as the list of files, size, and names. 10 in brackets. Servant. Combination of servant and client. In the old centralized file sharing model, there will be distribution of information servers, requesters of information clients. In the decentralized Gnutella model, each computer on the network is both client and server and thus called a servant. 10 in brackets. TCP/IP, abbreviation for Transport Control Protocol Internet Protocol, is internet communication protocols between hosts. Time to live. Time to live is TTL is the number of hops that the message will make on the Gnutella network before being discharged. Each servant that views a message will decrement its TTL, the time to live, by 1. Will discard that message when the time to live reaches 0. This prevents a message from being sent back and forth across the Gnutella network. Definitely, most Gnutella clones set TTL, the time to live, around 7, although some allow the user to configure it. 10 in brackets. Methodology. This project will apply the Unified Modeling Language, UML, to model the application's design process. The ULM, the Unified Modeling Language, uses a set of graphic notations to represent processes and concepts. Bracket 11. In brackets 11. These UML, Unified Modeling Language notes are useful tools to represent the message communication between different objectives in the development of OO software. Conceptual modes and sequence diagrams are widely used in this project. Sequence diagrams are described how objects collaborate with each other. They give dynamic views of the object. Sequence diagrams are detailed how operations are carried out, i.e. what message is being sent and when. Sequence diagrams are organized according to time. Time progresses down from the top of the page to the bottom. The objects involved in the operations are listed from left to right according to when they take part in the message sequence. There's another interaction diagram called a collaboration diagram. It conveys information similar to a sequence diagram. The only difference is that the collaboration diagram emphasizes the role of objects, while the sequence diagram focuses on more than on time sequence. In this project, because a time control is applied, it is better to use sequence diagram rather than the collaboration diagrams. The project puts more focus on the system modeling rather than the software implications. Therefore, the conceptual model on choosing the model system concepts. A conceptual model is representative of the concepts in a problem domain. In the UML, a conceptual model is illustrated with a set of static structural diagrams in which no operation is defined. The terms conceptual model has advantages of strongly emphasizing a focus of domain concepts, not software entities. It will show the concepts associated between concepts and abbreviations of concepts. 11 in brackets. Outline. This project consists of 6 chapters. Chapter 1 is defined as the common technology and describes the methodology. Chapter 2 provides a background about peer-to-peer type applications. Most of the focus on the comparison between Napster type centralized application and Gnutella type decentralized applications. A Gnutella protocol is introduced to explain how this application will work using the message exchange. Chapter 3 presents a problem in the Gnutella type peer-to-peer application and ways to solve these problems. Chapter 4 presents Gnutella type P2P application system functionality and architecture. Chapter 5 describes a specific application model using the UML sequence diagram and our explain message follow the state how the functions are fulfilled. Chapter 6 gives a summary of this project and how further efforts might redefine this project. Chapter 2, background. Napster, the music sharing system, has been the focus of controversy and has faced the consequence of being shut down. The file sharing storm that began with Napster will never end. Thousands of users at home connect to each other and form a network with search capacity in the virtual internet world. Napster is a peer-to-peer application with central controls. There are central servers that store the file directories where the queries and connection brokers are taking place. Once the end-user computer finds a data destination through the searching the directory, file sharing will occur between these two machines directly. Napster is performing a combination of peer-to-peer file sharing and centralized indexing by centralized directories and decentralized content. Napster couples the strengths of the central database with power of distribution storage. Napster has become the fastest growing application in the Internet's history. To meet the needs of a pure decentralization without central server control, many decentralized peer-to-peer systems have grown up and tried to create a Napster replacement. These alternatives include Gnutella, Freenet, Ohaha, and Freehaven. Each of them has a different focus to address a variety of issues existing in the decentralized network. A peer-to-peer network without any central control means each node in the network is equal. Each node could be both the server and the client. In new terms, servant has been created to name this kind of node. A servant is able to concept connections to provide services while it is accessing another servant to retrieve data. Each servant is free to join the network and free to leave. Assessing these decentralized resources means operating in an environment of unstable connectivity and and predictable IP addresses, that is, the characteristics of the type of peer-to-peer networking. All works based on peer-to-peer network must tolerate this unpredictability and must know how to deal with it in order to do useful things. Peer-to-peer decentralized file sharing systems without centralized storage and authority is proposed. There are several challenges in decentralized systems. One, in providing search capabilities without central storage is very expensive to index and make data available easy. Second, each computer on the network is a client that downloads files from other machines. In the meantime, it is also a server that provides the file download service to other machines. Third, it is not easy to locate a serving machine in an unstable environment because these machines can leave and join without notice to prior configuration. Gnutella is one of the first of many decentralized technologies that does not rely on any central authority to organize the network or to broker transactions. It was developed in March 2000 by Justin Frankel and Tom Pepper and was released as an experiment. Later, open source developers intervened. A developer, Brian Malin, reverse engineered Gnutella's communication language and published his findings, known as the Gnutella protocol, on Gnutella's website www.nerdherd.net. Gnutella network developed benefits from the Gnutella protocol and open source approach. Using Gnutella technologies as a servant can connect to any of the arbitrary hosts. The connection can be made and one can start working with the other Gnutella node. At the beginning of the Gnutella technology development, an arbitrary host IP address discovered when one wants to connect to the Gnutella network. Now the host IP address and port numbers are remembered and stored in the end computer, and the end computer will cache and host used in last connections, and host can be reused for the new connections. This technology can make the Gnutella node connect to the Gnutella network automatically. JTella as the Java API for Gnutella network developed by Ken McCary. It provides a network interface for Gnutella-style server application development. JTella is an open source to the public interest in Gnutella servant development. Protocol description. A Gnutella protocol is a development by the CP2 company, www.cp2.com, to centralize the development Gnutella-style servant and application. This protocol describes the specification that a peer or servant should implement what he wants to participate in a Gnutella network. To accomplish data exchange, the Gnutella communication system is based on the message-based application level routing. There are 5 message commands being proposed: ping 1 ping, used to actively discover host on a network. A server received a ping descriptor is expected to respond with one or more of the pong descriptors. 2 pong. The response to a ping includes the address of a connected Gnutella servant and inform regarding the amount of data that it's making available to the network. 3 query. The prime mechanism for search and distribution network. A servant receiving a query descriptor will respond with a query hit if a match is found against its local data set. 4 query hit. Response to query. This descriptor provides the receipt with enough information to acquire the data matching the corresponding query. 5 push. A mechanism that allows a firewall servant to transfer file-based data over the network. The Gnutella servant performs tasks normally associated with both client and server. They provide a client-side interface through which users can issue queries and view search results. At the same time, they also accept queries from the servant, check for matches against their local data set, and respond with application results. The command message list above route throughout the network. The underlying protocol, the TCP IP, and the Gnutella servant connects itself to a network by establishing a connection with a servant currently on the network. The connection is established through sending the messages to a neighboring servant and participating in the handshake. Once an address of another servant on the network is obtained, Gnutella connection to the servant is created, and then any one of the above command messages can be sent to create a transaction. Related works, there are a few well-known ongoing peer-to-peer projects. Freenet. Freenet is a project that focuses on the omnipotence of the data provider and digester, in brackets 8. Data are replicated adaptively and are stored in many nodes in the network, and data are inserted accordingly to hashing location independent key and up data in the local routing table. Data search requests are routed to most likely neighboring hosts according to the key in routing table without broadcast the search request. Ohaha project. The Ohaha project uses the consistent hashing function 7 using the same mapping function. The available data and query about the data are all hashed to a certain managed item ring. With a node wants to query for a particular data item, it will be able to commute and data locations locally using the same mapping function. Chapter 3, Problems and Solution. Problems. 2 problems are presented and solved in this project. The first problem is ping-to-pong broadcasting. A Gnutella network is very dependent on the message broadcasting in the connection stage. A servant pings the network. After a connection is established, the servant will ping the network periodically to maintain the connection. Each servant with the ping TTL limits answers with a pong message through the ping-pong approach. The Gnutella servant will get the IP address of the servant and establish connections with them. The ping-pong approach consumes 50% of the bandwidth of the total Gnutella message bandwidth, the IG4 in brackets. It cuts the Gnutella network performance in half. Without this message or these messages, more servants could be searching using the same bandwidth. Second problem in query. There is no central server that saves the index and metadata about the resources available in the network. A search in the Gnutella network is likely to crawl on Gnutella hosts with the Gnutella network. Like the pings, the current query in the broadcast, a host with the horizon view of the servant. Again, this consumes a lot of bandwidth. Solution. To alleviate the pain of ping-pong broadcasting, the key idea is caching pongs to avoid broadcasting pings too rapidly. There are 3 techniques to limit message broadcast traffic in pong limit: pong caching and ping multiplexing. Pong limiting. First, the host should only send a pong with its own address if the host is not firewalled and can currently accept incoming connections. Second, a host should only route a fixed number of pongs in response to a ping, so pongs should be enough to help hosts connect quickly. Pong caching. By caching the recent pongs and avoid broadcasting the pings, hosts can rely on ping caching, cached pongs instead of broadcasting the pings to ensure that hosts get fresh pongs, and importing that the cache expires every few seconds. Ping multiplexing. This technique will multiplex many incoming pings into a single outgoing ping, and conversely demultiplexing an incoming pong message into multiplexing outgoing pongs. To solve the problem of broadcasting a query, it is possible to cache, but it is not easy to control in this project. A URL search cache is used when a node receives a query and search to a URL cache is performed. If nothing is found, then it will perform the normal search procedure. A local search results set might be inserted into the LRU cache when the local search result is obtained. A non-local search result might also be copied in the URL cache for answering future queries when a node forwards a reply to other nodes. This approach saves a large amount of bandwidth. In addition, will simply broadcast the search request to the network directly, but the LRU cache should have a living time limit to keep the results fresh. Chapter 4, System Operations. General description. Until a network by virtual propagation, each node plays a role relaying against by passing a received message to its neighboring nodes every time a node about its neighboring nodes by establishing connections with them. A node sends a message to neighboring nodes, and the neighboring nodes will send it to their neighboring nodes. A node only needs to communicate with the neighboring node about the rest of the network. In a single Gnutella network, there is no physical circuit to connect to the nodes together. All nodes are dispersed in virtual internet. To set up a connection, a node can randomly pick up any host IP address collecting during previous connections and store it in a cached file. If node A is established in an Gnutella connection with B, then B is called nodes A neighboring node. Every node has a set of neighboring nodes to communicate with them. A node communicates with its neighboring node by sending a Gnutella message that contains descriptors defined in Gnutella protocol. Gnutella network is an open network. Any node that speaks the Gnutella language, Gnutella protocol, can connect to the network anytime to exchange. In the same manner, any node can leave the network without prior notification to the rest of the network. If a node is disconnected from the network, its neighboring node will passively detect this event, and next time they send a ping message, every second there are a different number of nodes working in the network. That is why Gnutella Network has adopted the message broadcasting mechanism. The Gnutella functions like an Ethernet. The Ethernet only manages a small number of nodes using the broadcast mechanism. The Gnutella network has a huge number of nodes, and a single generated message will produce an explosive number of messages. Traffic is being an issue in the Gnutella network. For example, the Gnutella network, each node contains 10 active connections with TTL value 7. In the worst case situation, a single broadcast message results in 10 million 10 to the 7 messages. To minimize the unnecessary broadcasting message, and all reply messages will be routed back to the appropriate originator. But the Pong message is no longer routed. Each message contains a GUID, which allows Gnutella node to uniquely identify each message on the network. Furthermore, every node can tell if the message is reply message to the node or just pass by message by the message guide. If two request messages have the same guide, the layer 1 should be discarded. Each Gnutella node maintains a ping router routing, a search routing table, and a search replying table to remember the message guide it is forwarded to in the project. The Pong is a demultiplexer. Instead of being routed back, the search reply message and the push message will be forwarded back. Architecture. Gnutella network has no hierarchy. Every servant is a servant and a client. Each one is expected to contribute figure 1. All that good is right there. Figure 1 Gnutella architecture. Theoretically, in a Gnutella system, the servants are equal, but in a real Gnutella network, some servants have made more stable and faster connections to network, so they can support more traffic and can act as a hub to other nodes. Therefore, they get their request answered much more quickly. Servant running on a slow and vulnerable connection finally connected to the fast connection nodes to contribute and download after the network starts. Eventually, it will evolve to be an adapted form as shown in Figure 2. Figure 2 is an effective Gnutella network. Right there. Each Gnutella servant only knows about servants it is directly connected to. All other servants are invisible unless they announce themselves in answering to ping or by reply to a query. This provides amazing anonymity. System function, ping-pong scheme. Gnutella ping-pong message serve two functions. First, the ping-pong mechanism returns IP addresses of other servants, so more connections can be established. In case a peer disconnect from the network, other peers connecting to this peer can find other peers to reconnect to the network. Second, it provides a measure of horizon size, i.e. the number of searchable hosts and files, in reply to ping message. A pong message contains information about peers such as IP addresses and ports, as well as numbers of files shared on the total size of those files called payloads. In brackets 4, ping is used to discover hosts as a pong contains host information. The pong scheme serves a very important function by keeping a servant connected to a Gnutella network. The trade-off is because it consumes so much bandwidth, it degrades the performance of the Gnutella network and uses substantial internet resources. 3. The ways they use to improve the performance of ping-pong approach. 2. Pong limiting. When the connecting request comes in, if a host is not firewalled, it may accept the connecting request and establish connections between these two hosts. Once the connection is established, a pong responds to the request node in reply to ping. In addition, it will only forward back a mix of pongs from the answering nodes. To answer this ping, each reply contains a hop value which counts the many hosts it has passed through. Those pongs will represent the distributed host range measured by message's hop value. In other words, it will respond to ping and a pong message contained in the particular hop value required by a ping message. 2. Pong caching. Pong caching is another way to reduce network traffic. And the key idea behind the pong caching approach is to avoid broadcasting the ping result if there are fresh pongs available in the local host. These fresh pongs can be reused to address these ping requests and thereby reduce the repeated broadcasts that might go through the same route in a short period of time. Figure 3. Back there. Figure 3 is pong caching diagram. Host A connects to host C, and host A sends a ping to host C. And then the several pongs then the disconnect to C in a very short time. 4 connect to C, then ping to request to C. If C and number to a stable connection, this new ping request to absolutely get to the same result like P's, but they're A's. Request previous. If the previous ping consult to cached in C, then C could request to cache results without broadcasting new ping and save broadcast traffic. To avoid answering an outdated cache and keep cache dynamically fresh, the pong cache reflects to a few seconds and reflect to newly connected to disconnect host state and network. Hope the ping cache expire and broadcast in ping request to its neighboring host. If the host adapt to same cache approach, they may respond to cache pong answer this ping. 3. Pong multiplexing. Extreme case, if the host and no caching pong to the cache pong expire to a host receive more ping in almost same time. In this situation, the host should only send out a ping request in multiplexing all these pings. When the pong is back, the host will demultiplex and single incoming pong to multiplexing outgoing pongs. Initialize the Gnutella connection. Into connection to the Gnutella network, the servant will initiate the handshake to host the particular port. Basically, there are two-step in handshake process. First, the servant will make a HTTP IP connection to server. And the connection is set up. The server sends a Gnutella section request such as Gnutella connect /auth4 \n/n. Accept the server concept except that the connection request and response, the Nutella OK \n \n. At this time, a Nutella network is established and connect server become one of the Nutella network members. It is ready to participate in the Nutella activity like searching, download file, etc. Being to Nutella network, because there are no central server available to initialize the conversation, a Nutella server will connect to one of the publicized hosts and are almost always online. The host will introduce the Nutella server to host by broadcasting this new IP address in the port number. Figure 1. An example to depict how the new host connect to the Nutella network. Imagine a node Z and try to connect to a Nutella network that contains all the nodes A to Z. Assume the Nutella network of Y had been established between node Z. Node A is in node Z status to maintain the connection Y data. For node A connection, Y represent node Z. Connection Y contain the 3 variables. The 3 are last ping time PT, and the 2 is the guide P, the GUID, and then the space and then the P. And then the desired Pong array need the Roman numeral I. I is from the 1 to M. Okay, so now we got the time, the PT indicate that the ping connect to Y except by Y. A, the guide, the GUID variable P store the last ping guide from the connection. The Pong expected amount of array need. In the brackets, they tell you how many Pong are needed to connect from 1 to the TTL. All need brackets, remember, into initialize to M. The total maximum expect Pongs from A to Z is M times the TTL. Need a bracket to call the demultiplexed multiplex table and will be used to demultiplex the Pong message to the specific node. Each node maintain a Pong cache. In the brackets, a cache expiration timer. This is the ET figure 4 to show the ping pong flow. 1, we got the node Z send a ping message to node A with guide X. And we got the figure here, the ping process is the figure number 4. You see here, you got all the information you need. Okay, we look at that. Okay, the ping goes from the Z to the A, the ping, and then the ping right back. And then you got the PT is greater than the CT, it dropping the ping. You go to the ping after the A to Z ping. And then from the A, you got the CT is greater this time than the ET. And then from the Z to the A ping, we go from the C is greater T to ET. That means that the CT is equal to CT plus T, broadcast ping to update cache in bracket. And otherwise, we got from the Z to the A ping, go from the A, otherwise, when you get the Pong back, in the final process, you get the Pong back. Initializer, we got the need in the bracket. You save the ping guide as X in the variable P. That means the update PT equal PT plus T. Okay, very simple, very simple. You ping, and then you expect to get the Pong. Okay, we get the update PT equal PT plus T. Okay, update ping routing table, guide X, connect to Y. The connection is to Y. Generate to the on ping, connect the node A IP address. It send the corresponding cache in the bracket. It comes to the ping. Okay, you understand? I'll show you the diagram one more time. This is figure number 4. Okay, 2. Node A will check a PT and current timestamp a CT. If PT is less than CT, this ping message will be discarded and prevent some node from sending the ping too frequently. Otherwise, the PT equal to PT plus T. Okay, we got the number 3 here. The node will compare the current timestamp CT and expect Pong cache expiration time ET. If CT is greater than ET, it means that a Pong cache expired, and then set up a new expectation expiration time. CT equals CT plus time. Okay, number 4, we got the connection node Z's. Set up the Pong multiplex table needed. We got that in brackets, so the record how many Pongs it need. Save the guide X in variable P. And the 5, we got the node that hook up in the ping routing table for message guide X connection Y through comparing the message guide. If the message is not the ping routing table, save message guide X connection Y. The ping routing table otherwise to connect the message in the loop routing will happen to be dropped. 7. Respond to ping message with same guide X to node Z through connect Y. 8. We got the Pong cache not expired. Node A, look, it's Pong cache is cached in the brackets. Each cache element list of Pongs is send the needed cache Pongs to node Z according to multiplex. Need table. Data multiplex table accordingly. Then the new Pong come back. It come back a Pong connection as needed. Number 9, if Pong A Pong cache expires, it needs to broadcast node Z's ping request it to all neighboring nodes like node B, node C, node D. 10, we got some node B respond to one Pong message and reply to this ping. And node A to add the Pong message in Pong cache array. This will also be demultiplexed the Pong message to node Z by caching its multiplex table to connection Y. It need more Pong. You see, it need more Pong. Node A will forward the Pong message to the last ping guide X, so recording in connection Y to node Z. So node Z can match a Pong to message in the original ping message through the guide. Node H receive a Pong message A twice, that's 2 times from router ABH and route ACH respectively to prevent a loop and ping. So ping message guide resists exit the ping routing table. This ping message be dropped without forwarding, like ping to H. Either message arrive first, ping routing table be updated. Another late duplicating ping arrives, it will be dropped. You see the notation figure 5. We got the looping ping process diagram. I'm going to show you now. Yeah. For the messages control variable TTL, the variable hop, that is similar to IP routing concept. The TTL control how many hosts the message can go through before it dropped. Basically, message is sent is stamped with the TTL hop and the message arriving host. The TTL decrement is the hops will increment. If the TTL becomes 0, the message is dropped and the hop mainly used in the data demultiplex table. Okay, I'll show you the diagram one more time. It's a figure. Loop P-Pong process diagram. Okay, I'll show you. Okay, it goes Z Pong X, ping XB, ping XH. They go flow to the right. You got also in the lower hemisphere, we got the Z to the ZX ping to the A, and A goes a ping out one more time to the C, now follow ping out to E, but then an E go to the H, but also the B go to the H, so they both figure their own route. You see which route go faster, you see the top route go one less, it do one less. Ping X from B, okay, go, and wait back for the Pong, same thing down the bottom here, and go ping X from E, so ping from B, and then ping from E. It's trying to get to H. Assume a ping from the route the ABH arrive here first. Host H. Check the ping routing table. It's a ping routing table. You see? You see, it's so simple. You look at it. You see this simple. One less. It goes this way. Go faster. Now check the ping routing table. Guide X is not found. Then the host reply ping is for ping X. Guide X to be recorded in the ping routing table. You see, it's so simple. So because the ping X and the ACE arrived later than from the routing ABH, host H will find guide X has already ping routed in table and will be dropped. You see, I say so much, but it's one extra step. It goes the shorter route. Query data. When the nodes search the Gnutella network, it sends the query message to all its neighboring nodes. And the nodes contain the files and match the query criteria. It should answer the query, otherwise it will discard the similar silent, forward its query message to its neighboring nodes. In each node, the query cache is applied to improve query performance. When the host arrives at the query request, it first checks if it is matched record in the cache. If one exists, it will respond to the cache record. Otherwise, it will perform a search locally. The cache is the LRU cache. Every time the query records is found in the local host, the query records will be inserted into the cache. When the cache is full, the oldest one will always detect the new record in this insert. When the cache record is found, it will be marked as a new record, and when the host forwards a query result, it will add record to the cache. Every record has a lifetime after the period time. The record will be marked as dead to prevent the host from returning as disconnected host as in the search result. Since the Gnutella network is a dynamic network, some hosts disconnect to a host and some hosts connect to the network every second. Sharing data. Theoretically, each of the connected computer is expected to contribute some file for sharing. Some not obligation to it is desired. Sometimes the computer joined to a Gnutella network with nothing to share. It share nothing. This problem calls for free riding problem. Because the free ride computer consumes same resource for the computer that are computing. Some computer server implications filter free ride computers out of the network, outside. Data sharing indication data available to search and downloaded by other nodes. Downloading data. Downloading file servers use the HTTP protocol. The downloading clients request a file is sent by the following message stream: get /lowercase get /1234 /hello dot lowercase uppercase HTTP /1.0 \lowercase r \lowercase n connection keep capital K lowercase eep /uppercase L alive /lowercase r \lowercase n range bytes equals 0 /1 /r /n /r /n. I'll show you now. You see your eyeball. The range parameter for resuming partial download 1, 2, 3, 4 is the file index number, and it says hello.dat is the file name. The server will respond with normal HTTP header, for example, HTTP 200 OK /r/n. Server Gnutella /r/n. Connect time application binary /r/n. Content length 948 /r/n. And then /r/n. One more time, last time. The connection length header indicate how much data to expect after it received the socket closes. Chapter 5. We're getting closer to the end. Chapter 5, we got one more chapter after this. We're done. Chapter 5, System Design. Class definition. Gnutella server consists of a network layer and a file server layer, and the network connects to the other host to maintain connection with the Gnutella network. It consists of 7 components. They are 1. Gnutella connection, 2. Incoming connection manager, 3. Outgoing connection manager, 4. No connection, 5. Router, 6. Host feed, and 7. Host catcher. The file server serves to search, share, and download data The server layer consists of the search manager, file manager, share manager, download manager, and monitor. Network layer component, incoming connection manager. The incoming connection manager lists on a port. Whenever a new connection is attempted, the no connection object is implemented and stored in a connection list object. When the node leaves the Intel network, the network neighboring node will need to clean the connection node. Incoming connection manager is responsible for removing dead connections from the connection list object. Outgoing connection manager. When the node connects to the Intel network, it will maintain a certain number of live connections and its neighboring nodes. In some case of the neighboring nodes leaves the network, some connections become dead. The network connection manager extracts the host/port pair of the host cacher to make more connections to satisfy the configuration live connection requirements. Node connection. Each node connection represents a Nutella connection and a neighboring node. A node connection will keep reading from the connection input stream to form the income manager message. The message is then added to the router's message queue. The router takes the message to process accordingly. The router takes responsibility to deliver the message according to the message type. Usually it broadcasts a request manner such as a ping message or a search message to the neighboring nodes if a cache is not available. For a reply message or push message, it will route it back to the original node if the message is in reply to message orientating from the node and the message is sent back to the associated handler to process. There are 5 typical kinds of message types: ping message, pong message, query message, hit message, and 5 push message. When a message arrives as a servant, if it is a request message such as a ping or query message, the router must first form the servant on a reply message such as a pong message or query hit message to the answer request servant. After that, the router will determine whether they broadcast this message to its neighboring node or picks up the cache if the cache is available. If the query hit message is received, it must first look up its own query routing message to find out whether this message should be sent. If a push message is received, it should look up the query hit routing table to find out where to send this push request message. If reply message is servant sent, this means that the reply message is responding to requests originating from the servant. The router must wake up its listeners to receive the process. This process message, reply message, will not be routed anymore and will end here. If the pong message is received, it will insert into pong cache its connection, checked with the demultiplex table, and then forward to the nodes that needs pongs. A received search message will be sent to the file manager to search locally. Host feed. The host feed attempts to detect in the Nutella network. It periodically pings the network host catcher. The host object stores the host port's pairs and later is read by the outgoing connection manager. File server layer component. First, search messenger. The search messenger generates the search criteria, creates the search session, and pairs this query hit message, receives the stores, and researches so that the download manager can download these files later. First manager, or file manager. The file manager serves the search from other nodes. When a search message is received, the file manager will perform a search in its search cache and then search file list. If found, file manager creates search reply messages and sends out to nodes that generate this search through the router. Download manager. The download manager does 2 things. 1. Push request management. 2. Download management. 3. File host has no firewall protection. A normal download can be executed. The download manager creates a download thread and then the HTTP connection to download the file from the host. The file host is protected by a firewall and the request host is not protected by a firewall. A push download can be executed. The download manager creates a push request to the file host. ask the file host to create an HTTP connection to this local host, and then file connection download can then be carried out. Monitor. The monitor is logging the servant activity in the Gnutella network. It pairs the query hit and displays the query message on the console so people can see what other people are looking at. The service controller. The service controller represents the Gnutella servant interacts with the end user. Starting up the servant is an instantaneous service controller class. The server controller then sets up the user interface, initializes the network layer and server layers. The work threads are created and connections are then established. The class protocols in Figure 6 the overall class protocol diagram, where it goes from monitor and shared manager. They both create the service controller. There's a file manager and a download manager that link to create into the service controller. And then you got the networker and the search manager also connected to the service controller. So everything is connected to the service controller. So those are triangles there, but everything is just a one-to-one link. See the ones? That's what the ones mean. It's called a overall class prototype diagram. And these figures here, they explain the definition between all the descriptors in here, and I'll read that to you. Okay, the share manager private vector dares to share, private vector files to share, private hash table numbers to files, private hash table names to files, private vector exclusion list, private vector inclusion list, private hash table index files, private int total file size, private vector to upload list, private int to upload count, private hash table mine type mapping, and then private boolean, the rescanning, the Booleanian algorithm search engine. This is all under the share manager first bracket here. Okay, and just below that is the share manager section. Under the share manager, we got the public void set shared DRS strings, the DRS. The public strings get shared DRS. The public void adds shared DRS string dir. Public void removes some DR string DR. Local voids remove shared DR. Intent I. Public sharing files get file index int. Public sharing file get file integer file number. Public integer get total file size 0. Excuse me, there's no 0. Private int find share directory string directory, and then we've got everything's coming out of the service controller. By the way, each one of these boxes I'm reading, everything's coming from the service controller. Got the connection manager. There's a private int desire connection count, protected connection list, private Boolean shutdown. That's the algorithm used to search things. It's an advanced Boolean search code. Private connection data, protocol router to router, not top section. Within the connection manager, you also got void set. This is the subsection. Void set desire connection count, int get desire connection count, void shut countdown, Boolean is shutdown, connection list, get connection list. bottom here, file manager. Upper bracket we got, or upper box we got the private GNutella connection, private static search cache. Bottom section here you got the public file manager, GNutella connection, network connection, public void insert search cache reply message M, public void receive push manager push message, void set file server session, server session. This is figure 8, the overall object model diagram. The top section here, remember every one of these boxes is coming out of the server control. You got the search manager, private Nutella connection C, private static vector reply list, private static int port, private static sharing IP address, private static int speed, private static guide. In the lower section, public search manager, GUNT, that is the uppercase, Nutella connections, network connections, public void search, string, search start, str, public vector get reply list. And we got the download manager. Remember, everything's coming out of the server connection. It's a one-to-one connection that leaves the server controller. It's a 1, see all the ones here? And it initiates all these programs here. It initiates this type of process. It originates from the server controller. I got the download manager, private vector M download list, private hash table, M pending push transfer, private int M worker count, private boolean M shutdown all workers, private int M downloading count. In this lower bracket we got the download manager, void int publicly synchronized void creating enough workers. Synchronized boolean is too many workers. Public synchronized boolean add file T download or to download remote file R file. Publicly synchronized download file get next file to download worker. Okay, everything's leaving, initiating from the service controller. One more down here, we got the networker coming out of the service controller. That's the private host, private cache, private router, private incoming connection manager, private outgoing connection manager, private host feed, private search monitor section, search M monitor session. Lower box here is the public void stat, public host cache, get host cache, void broadcast, public linked, get connected list, public search session, create search session. Okay, lastly but not least, is actually the primary portion. Service controller comes from, everything's coming from here and initiates in a there's a one-time output here. That's a private JFrame Windex, private share manager, private search manager, private download manager, private file manager, and then in the lower bracket here, box here, we got the private, or the sub box, private void setup component, public Windex. We got the public void shutdown, void connection host, void search. And this is figure 8 overall object model diagram. Go ahead and pause it here. Okay, message flow. Connecting to the Nutella network. When the network Nutella connection starts up, it will start the host feed by passing a host and a port for handshaking. The host feed will first create a socket to known host, then it will try to ping the host periodically. The receive prong will send the PONG cache and the host cacher. The host cacher will derive the host and port number from the PONG. The outgoing connection manager will read the host port pairs and host catcher to create the node connection to these hosts. The new node connections are stored in the connection list and are ready to exchange message. The data between hosts and message flow is shown in figure 9. Figure 9, connection sequence diagram. We'll go over that. Routing message. Each incoming node connection will keep reading any inbound message from its input stream buffer. In queue, the message and router message queue. In the meantime, the router has running thread to read the message from the message queue and processes it. If the ping message and a pong message is generated immediately, the return to requester through the incoming node connection output stream buffer, the ping message will continue to be passed to the pong receiver to broadcast to all its neighboring nodes. If no pong cache is available, if the cache is available, it will respond to this ping message using the cache pongs. For the search message, it passes the search receiver in the file manager to process the search. For a pong message, the pong cache is updated for each connection. So the diagram here, figure 9, connection sequence. You got the actor, you got the controller, Nutella connection, host feed, socket, host connection, outgoing connection manager, router, node connection, connection list. Listed here all across the top, and streaming down below shows the actor. It's going to the controller to connect, and then it's going to the Nutella connection new, and there's a smaller lowercase new that's going to the host feed. And from the Nutella network, you got branching down, it's going out to 5 different locations, but from the top we'll go from the host feed to the new IP port to the socket, and it stops there. Also from the Nutella connection, it goes straight past the host feed and socket to the host catcher, stops there. And then the third line out of 5, it goes from the Nutella connection, skips over host feed and socket, and goes over host catcher, goes to the outgoing connection manager and stops there. So they're just going directly to where they need to go, kind of like that last diagram that we have. Also from the Nutella connection, is passing over the host feed socket, host feed and the socket and the host catcher, going over the connection manager, going straight to the router. Okay. And then here again, the last one for the Nutella connection, skipping over the host feed, socket, host catcher, connection, outgoing connection manager, router, Nutella connection. It goes to the connection list. So it's not skipping over, they're just taking different routes, but this is the way the diagram's shown. From the host feed, it pings to the socket, okay, here. And then from the host catcher, it goes from the router to the pong. That's the received portion. From the host catcher, you're sending out a message, and you're getting something back from the get host under the outgoing connection manager. Sending out a message past the router to the node connection, and it's adding, that's the new, and it's adding adding a message going past the router, past the node connection to the list connection. So that's what this diagram is showing. Figure 9 connection sequence diagram. It's actually really simple, just a little foreign at first. Okay, for a search message, it is passed to the search receiver in the file manager to process the search for a pong message. The pong cache is updated for each connection, except its incoming one. It will check its demultiplex table to see if any connection needs more pongs. For a reply message, the query routing table is searched so that this message can be routed back if it is not for the node. For a push message, the query hit routing table is searched to route to its host. The message flow is shown in figure 10. Routing message sequence diagram. Search data. Client side, the search manager will create the search session by passing the search receiver to the Nutella connection. The Nutella connection initializes the search session and returns the new search session object to the search manager. After this moment, the search manager could send the search criteria to the search session to perform a search. The search session sends a broadcast message to a Nutella connection. The Nutella connection retrieves the active node connections from the connection list. The send receive method in the node connection class then asks the router to store this message guide in the query routing table. Finally, this message is written into the node connection's output stream buffer. When the search reply message returns, the router will invoke the search reply receiver in the search manager. The search reply receiver will store the result in the search result object for a further download process. The message flow is shown in Figure 11. Server side, the file manager serves a search request for this host. Basically, when search message becomes in, the search receiver will be notified. The message receiver will search the cache first, then share file list to see if there is such to the search criteria. If there is, it will build a search reply message including the host port. Okay, for Figure 10, routing message sequence diagram. Across the top, you got the node connection, input stream, router, message queue, file manager, and output stream. I'll explain how the routing is. Okay, you got the connection node goes to input stream and performs its action there. The route skips over the input stream, goes directly to the router, and that in queues go to message output. Also, we have that connection node jumping all the way over to the output stream, and then furthermore we got the on the router. It goes to the read queue and it receives a message and sends it to the file manager. There's a router, it sends a message back, and here's a message that writes to the output stream. So this is Figure 10, route message sequence diagram. Figure 11, request search sequence diagram. On the top, you got the actor, search manager, Nutella connection, search session, connection list, node connection, router, output stream. Actor goes to the search, searches to the search manager, and that in turn creates this action here. It's more just like places it's hitting on the circuit board, and that bank in turns will branch out its program according. Okay, creates a search session, goes to the Nutella connection, and then that goes a new message to the search session. And from the search manager, we got it jumping over to the search session, and it sends back a broadcast message to the Nutella connection, and then that goes to the get active connection over to the connection list. Also, the Nutella connection send receiver to the node connection, and then that bounces a route back to the router. With the node connection, it writes a message to the output stream. And this is Figure 11, request search sequence diagram. Okay, the server side, the file manager serves a search request for this host. Basically, when the search message comes in, the search receiver will be notified. The search receiver will search the cache file first and then the file share list to see if there is a match to search criteria. If there is, it will build a search reply message and send to the host in a port. The payload index to the number and the file reply to the search, otherwise the message will be discarded from nothing will be done. The message flow in Figure 12, another figure, god damn it. Pardon my language. Somewhere here. Figure 12. The server search request sequence diagram. The download data. After the user performed the search result and received that met the search criteria, then the server chooses one specified file from the result set download. The file, once it is chosen, the server will send down request to host this file belong to. After handshake, the download will start. Sometimes the selection is behind a firewall, so not to be able to accept a connection. In this situation, if it's not behind a firewall, it will be sent back a push. Request a host, expect for remote host to initiate connection to the server and to push the file to server. The download manager receive a push. The download manager will use a host port and index information contain the push message to contain it to the start push the file to server. Wait for the file to be downloaded. Client side. Download manager receive a download request to download a file. Then set to a new thread, the download worker, which is dedicated to download the specific file. Download worker to create a new socket to prepare the download. After the socket is established, writes the HTTP request asks for final download. Once the HTTP request is retrieved, the download handshake is successful, and then the file download can start. The download worker creates a file buffer to store the file on the download disk. File is read from the input and written to the file buffer. The message shown, message flow, is in figure 13. But first we're going to show you the figure 12. We're talking about the server search request diagram. The top of file manager, all the way across the top. Search cache, share manager, share file list, router table, no connection, output stream. From the file manager, it goes to search to the search queue, bounces back from the search cache to the file manager. File manager also has a search go out to the share manager, and that in turn searches the share file list. The get connection goes to the router, and the router gets to the route table. From the file manager also sends a no connection, and then that writes the output stream. So that's figure 12, server search sequence diagram. Okay, server side, the download manager waits for a connection from the download request. A server socket creates to answer a download request. The download manager creates an upload thread by passing the server socket and uploads set input and output streams for the server socket. It reads the HTTP request and forms an HTTP request to answer the handshake request. After this moment, the connection is ready to upload the file to the requester. Download worker calls to get the file manager method to share the manager to read the file and writes the file to output stream the server socket. The message flow is shown in 14. Another. No more diagram. Don't want that. Figure 14, server download sequence diagram. Still got to go over 13. Okay, pushing download. Client side, download manager receives a download. A request to shut down a file. It will start a new thread to download worker, which it's dedicated to downloading a specific file. The download worker creates a new socket to prepare the download, but the socket creation is not able to complete this because the destination host is protected by a firewall. The download worker forms a push message and invokes the router to route this push request. The download worker threads and then sleeps and awaits to be woken up. When the push reply arrives, a new server socket is created. When a push reply arrives, the download manager wakes up and sleeps download worker's thread by passing the socket to it. The download worker writes HTTP request to the server socket output stream to ask for a file download. Once the HTTP file is retrieved, the download handshake is successful and the download can start. The download worker creates a file buffer to store the file in the local disk. The file is read from the output stream and writes to the file buffer. The message is shown in 15. Figure 15 request push download sequence diagram. Okay, we're going over figure 13 request download sequence diagram. These are the ones that were mentioned previously. Okay, across the top we've got the actor download manager, download worker, socket input stream, output stream, the buffer. The actor downloads to the download manager, and then from the download manager it goes to new, download worker, and then from the download worker to new to the socket, and then from the download worker I also got a new that goes to the input stream, and then from the download worker as well goes the write HTTP request to the output stream. And then from the download worker, read HTTP reply to input stream. Read file from the download worker goes to the input stream, and from the download worker goes to the file buffer. Download worker, write file goes to the file buffer. And this is figure 13, requested download sequence diagram. Figure 14, server download sequence diagram. Same setup we're talking about. On top we got download manager, uploader, socket input stream, output stream, share manager. Okay, it goes for this figure 14 server download sequence diagram. The connection goes to the download manager, and that download manager sends a new message to the socket. Download manager also sends a new message to the uploader. The uploader sends a message to the input stream as well as to the read HTTP request to the input stream, and then also from the uploader writes a HTTP reply to the output stream, and then also from the uploader get file goes to the share manager, write file goes to the output stream. So this is figure 14 server download sequence diagram. Okay, I think we left off at server side, so I'll reread this portion. Possibly server side, the download manager receives a push request. It then starts a new thread of uploader. The uploader initializes a connection and creates a client socket. The uploader sets up the input stream and output stream for this client socket. It then reads the HTTP request and then forms an HTTP reply to answer the handshake request. After this moment, the connection is ready to upload the file to its requester. Uploader calls the get file method of the share manager to read the file, to write the file to the output stream of the client socket. Message flow to figure 16 is shown in figure 16. Alright, let's show you that one. Figure 16. Server push download sequence diagram. Okay, sharing data. Sharing details what kind of information, i.e. which files is sharing and allowed to be downloaded by other servants. The shared manager sends a scan message to the shared directory. The shared directory will scan the files in the sharing directory and the index files by keywords. The index is saved in the share file list object. The search process will search the share file list object to look for the desired file. The upload process will look for the file index to locate the file directory. The Message flow is shown in figure 17. Let's do that. Figure 17, share sequence diagram. You got the actor, share manager, share directory, share file list. Actor shares to the share manager. Share manager scans the scan directory to add index to the share file list. This is figure 17, share sequence diagram. Okay, monitor. The route will notify the monitor receiver if a query hit is coming in. The monitor receiver then derives the search criteria and matches the records, and the derived information is then displayed in console, and the record is in the log file, and the message is shown in figure 18. Okay, monitor sequence diagram, figure 18. So that is monitor, monitor receiver, monitor session, Nutella connection, and the router. So monitor, a new message comes in, a new data comes in, that goes to the monitor receiver gets the new message. Also from the monitor goes to the monitor session. From the monitor, the set monitor session, monitor receiver goes to the Nutella connection. You have a monitor receiver that's receiving a message, and it's coming from the Nutella connection, and in turn it's coming from the router. So the router is sending back a file, monitor session, then in turn is going display to the monitor receiver. So that's figure 18, monitor sequence diagram. Figure 15, request push down sequence diagram. Download manager, download worker, client socket, server socket, input stream, output stream, router, file. Download manager sends a message to the download worker to the client socket, and the client socket is sent back a fail. The download manager is sending an accept, and that's routed back into the download manager. From this download worker, you got the data that's being sent to the router. Data you can also call a packet. It's a bundle of information, data. Okay, you have from the download manager, you got information new being sent out to the server socket, and it's coming back. And you have information going to the wake up socket, and that's going to the worker download. From the download work, you have a new message going to input stream, new message from the download worker going to the output stream. Download worker write HTTP request, TTP, going to the output stream, and also from the download worker read HTTP reply going to the input stream. Download worker read file going to the input stream. Download worker new going to the file. Write file going to the file as well. So this is figure 15, request push download sequence diagram. Fairly straightforward. Okay, figure 16, server push download sequence diagram. Like before, on the top, download manager, upload, socket, input stream, output stream, share manager. Push upload going to the download manager, new message going to the uploader to the socket with the new message going to the input stream, new message from the uploader also going to the output stream, HTTP request to the input stream, write HTTP reply going to the output stream, uploader get file going to the share manager, write file going to the output stream. That's figure 16, server push download sequence diagram. We went over 17, share sequence diagram. And we went over the figure 18 monitor sequence diagram. Okay, chapter 6, conclusions. Summaries coming up here. We got the Gnutella servant is an efficient tool for data interchange in the internet. Because it obeys the rules of the Gnutella protocol, it can exchange data with the existing Gnutella network. It also has its own advantage because it is able to cache data automatically. It is more efficient. If all hosts use this kind of servant for the data exchange, a great deal of bandwidth can be saved. The internet traffic can be reduced dramatically. Limitations of the project. There are many improvements that can be made to fine-tune the Gnutella network's performance. Adding cache capacity is only one of these ways to develop an excellent Gnutella servant. One might adopt an efficient random routing algorithm to replace the current request message broadcasting mechanism. Future work? Finding random routing algorithms that work in an unpredictable and unstable network would be a major improvement to the Gnutella network. Such a routing algorithm will route the request randomly. While it may not reach all possible servants in a single request, it could achieve a result that is acceptable. Recommendations? First, in order to design object-oriented software, the requirement must be researched and be fully understood. Second, a model methodology and tool must be wisely chosen. Our references are those are the brackets I was mentioning before, bracket 10, bracket 11, those are the main ones, bracket 10. 1. Orem, A. ed. Harnessing the Benefit of Disruptive Technology, O'Reilly and Associate, Incorporated, 2001. 2. Dingladine R and Free Haven Project, a design and development from an anonymous secure data haven available at http://www.freehaven.net/doc/freehaven.pdf/ less than value sign, and that is from 2000. Number 3. Clip 2, the Gnutella protocol specification v0.4. available at http://www.clip2.com less than, and that's from 2002. 4. Improvement Gnutella Ping Pong Scheme by Christopher Rose, LimePeer Technologies LLC, LimeWire, 2000. 5. Adar E. Huberman, B.A. Free Writing on Gnutella Xerox, 2000. 6. McCary K. and Gnutella File Sharing Network in Java World, 2000. 7. Smart Decentralized Peer-to-Peer Sharing Taking Gnutella FreeNet to the Next Level. Available www.ohaha.com of 2000. 8. Clark I FreeNet, a distributed anonymous information storage and retrieval system, University of Edinburgh, 1999. 9. Fowler M. with Scott K. UML Distilled 2nd Edition, a brief guide to the standard object modeling language, Edison Wisely Longman Incorporated, 2000. 10. LimeWire Gnutella software available at www.limewire.com, 2001. 11. Larman C. Applying UML and Pattern, Prentice Hall, PRT, 1997. Okay, once again that is Thesis QA 76 Z468 2002 Zoe Ruming, RUIMING, last name Zoe, ZHOU, a peer-to-peer application using Cache. That's Cache, C-A-C-H-E. It's been checked out 6 times. Once December 7th, 2004, December 6th, 2004, March 29th, 2006. Oh, I'm sorry, it's been checked out 3 times. Once December 7th, 2004, received December, whatever, RTD. Received December 6th, 2004. You got the wrong dates on here. Okay, March 29th, 2006, received May 30th, a day later. So that's supposed to be a day apart. Okay, also checked out February 26th, 2010, and received February 25th, 2010. The library code for CSU Chico Library, the barcode on here to look it up, to check this out, request the information. Go ahead and call the library and they'll help you out with that. It's 3 space 0 200 space 01563 space 0692. Replacement for this book if it's lost is $50. Chico Library. Thank you, Rumi Zhou. ZHOU, Spring 2002. Once again, our professors signing. It is approved by the Dean of the School of Graduate International and Sponsored Programs. Signature here, Robert M. Jackson, PhD, approved by Graduate Advisor Committee, Sung Bam Im, PhD Chair, and Melody Collin, PhD. And so can you. Today's date is September 10th, 2015.